you very much for this kind invitation. It's a pleasure for me to speak in the Bangalore Probability Seminar. So as Siva said, this is going to be a talk about the work of Hillel Furstenberg and Gregory Margulis, who were recently awarded the Abel Prize. So at the outset, I'd like to say that I can't really see the chat. So it would be nice if we could keep questions till the break, and I'll be happy to answer them during that time. All right. So it's a daunting task, to say the least, to try and summarize the work of Firstenberg and Margulis in 2 talks of 45 minutes each. So I don't think it's wise to attempt. So rather than try and squeeze in as many beautiful results as possible in this talk, I want to try to give a talk which advertises the area using some results of Firstenberg and Margulis. Okay, so Firstenberg and Margulis have immense influence in modern ergodic theory, and they've opened new vistas, connected or ergodic theory with different subjects. So I want to give some sense of how this came to be. And so I'll try to focus on 2 or 3 examples and try to explain how things are. Okay. So this is a picture of Firstenberg taken from the Abel Prize website, which also contains the following quotation, which about Firstenberg, which says that when he published one of his early papers, it was rumored that a single person couldn't possibly have written this paper, so it's probably Bourbaki-style pseudonym for a group of mathematicians, right? So it contains so many ideas that one person couldn't possibly have come up with. So that's Firstenberg. And here's a picture of Margulis, also from the Abel Prize website. And here's a quotation by Jacques Dietz on the occasion of Margulis winning the Fields Medal. And he said that it's not exaggerated to say that Margulis has on several occasions bewildered experts by solving questions that appear to be completely out of reach of time. Okay, so I'll start the mathematical content of the talk soon, but I wanted to give you one more funny quotation, which is Armand Borel on Margulis. So this is taken from an article by Li Zhenji celebrating the work of Margulis. And apparently, Armand Borel mentioned several times that Margulis caused confusion between the Borel and the Borel measure and Armand Borel himself, because he used both ergodic theory and Lie theory simultaneously. And apparently he also declared that he was not related to the other Borel, just Emil Borel. Okay, so this is just a few snapshots, quotations, celebrating the work of Firstenberg and Margulis. So before I begin, I also want to show you a picture taken from the collection of Anatole Katok. So I apologize that I couldn't center the picture, but I hope you can all see it. So this is a picture from the early 1960s from Moscow State University. And on the right-hand corner, you can see Anatole Katok. And on the very left-hand corner, this very, very young gentleman here, this is Gregory Margulis. Okay. And there's also David Kajdan in the first row left. So it's a really beautiful picture, which was also printed in the notices of the AMS article commemorating Anatole Katok. So I quite like it, so I thought I'll share it with you. All right. So both Firstenberg and Margulis started their mathematical work very early. Firstenberg, when he was an undergraduate, wrote a beautiful paper where he gave a so-called topological proof of the infinitude of primes. I first encountered this proof when I was an undergraduate from this book called Proofs from the Book, which many of you must have seen. And it's a beautiful little argument. And, we saw Margulis in this picture. So what was Margulis working on? Well, he and Kajdan were working on a proof of Selberg's hypothesis, which they both published when they were very, very young. So both Tristenberg and Margulis made a name for themselves quite early, and then really went on to create some beautiful mathematics. So in giving a talk about Firstenberg and Margulis, I tried to find some common themes, common threads, which I could explore in this talk. And thankfully, that's not a very difficult task. There are several major common threads running through the work of Firstenberg and Margulis. The first of these is the idea of rigidity in dynamical systems. So this is an idea which I want to convey today. And this is something which both Firstenberg and Margulis have studied intensively over the years. The idea that dynamical systems, dynamical systems, and we'll come to some examples shortly, are for us, they are going to be, they're going to comprise of a topological space or a measure space and a group action on this measure space. And this group action is going to be quite complicated. Okay, so nevertheless, a kind of recurring theme in the work of Firstenberg and Margulis is that there are surprisingly rigid phenomena in this world of group actions on spaces, on topological and measure spaces. So that's one theme I want to explore. The second theme I want to explore is connections to number theory. So one of the things that both Firstenberg and Margulis did was really open up ergodic theory and provide applications to really long-standing problems in number theory. So this is something which I want to give you a glimpse of as well. And finally, they're both known for connecting ergodic theory to probability theory, especially random walks on various interesting homogeneous spaces and so on and so forth. Indeed, the Abel Prize citation says that they were given the prize for pioneering the use of methods from probability and dynamics in group theory, number theory, and combinatorics. So my purpose today is to try to give you a glimpse of what this citation means in terms using some simple examples, and hopefully that will also spread some, provide an advertisement for this beautiful subject. Okay. All right, so let's begin with some of the main achievements of Firstenberg. So Firstenberg was instrumental in introducing ergodic theory into combinatorics. Okay? So we are going to see Semirati's theorem later on in the talk. Firstenberg provided a new ergodic approach to Semirati's theorem, and this really revolutionized the area. Okay, it was the forerunner to many beautiful results, culminating, of course, I mean, not culminating, but among the highlights recently, of course, the work of Green and Tao and Ziegler and so on and so forth. So a lot of their work can be said to have origins in Firstenberg's beautiful ergodic proof of Semirati's theorem. So Firstenberg is also known for introducing non-commutative methods in ergodic theory. He studied products of random matrices. One of his early beautiful results was on the unique ergodicity of the horocycle flow. So this was in the 70s, and we're also going to discuss this. So Firstenberg and Dani and Beach were made, the early studies and proved beautiful results for rigidity results for the horocycle flow on objects like the modular surface. So we're going to see more of this. And then this was the precursor which led to the famous conjectures of Raghunathan in the topological category and Dani in the measure category. which really were the main conjectures in homogeneous dynamics for a long time, till they were settled by Marina Ratner in the 90s. So an early example of the horocycle, of the rigidity of the horocycle flow was provided by Firstenberg. Another fundamental idea, which we are also going to discuss due to Firstenberg, is the notion of disjointness in dynamical systems. Okay, so he really formalized and provided spectacular applications for the notion that it's a two dynamical systems which exhibit different behaviors. So one, for example, which is uniquely ergodic, and one which is many periodic orbits. These two dynamical systems should not have anything in common. They should be disjoint. So he really introduced this beautiful idea, and this is proved to be very influential in dynamical systems. Also, Firstenberg is known for fractal methods in ergodic theory, and so on and so forth. The list goes on and on. Okay, so it's as I said, it's more or less impossible to try and summarize the work that Firstenberg or Margulis have done. To try to do both together is just out of the question. But these are some of the main things Firstenberg is known for. And now we move to Margulis. So Margulis, of course, as we saw, started early with this beautiful work with Kashdan. And then he was known, he won the Fields Medal for his famous theorem on the arithmeticity of lattices in semisimple Lie groups in high rank. Okay, so this was a very important open problem at the time. And Margulis won the Fields Medal for it. So we're not going to discuss arithmeticity and superrigidity today, but essentially it's a really striking result. So in a very colloquial sense, it says that if you take the group of the special linear group, the group of n by n matrices with real entries and determinant 1, this has a sort of a special lattice, which is the subgroup of integer lattices. So we'll come to what lattice is shortly, but it's a discrete subgroup, and the quotient is more or less compact. So it has a finite invariant measure. Okay, so by a famous theorem of Borel and Harishchandra, taking integer points provides very nice examples of lattices, and Margulis proved the landmark theorem that in fact in a high rank semisimple Lie group, irreducible lattices have to be of this kind. So they have to be arithmetic. It's a very striking result. And then we move on to another of Margulis's spectacular results, which is goes by the name of Oppenheim's conjecture. This is a conjecture about values taken by quadratic forms, and I'm going to talk about this a little bit later today. So it's a beautiful story. It was a long-standing conjecture on quadratic forms, and it looked like it was one of these things which Jacques Stitz was talking about, which it looked like no one could do it. But then Raghunathan came along and actually noticed that Oppenheim's conjecture can be reformulated in purely dynamical terms. So this was a very striking observation. And once it was recast into dynamical terms by Raghunathan, Margulis was able to prove this result. Okay, so we are going to talk about this a little bit later. In a completely different line, seemingly completely different line of work, Margulis has worked on combinatorics. So he's responsible for the first construction of expander graphs. So these are graphs with very good, very efficient graphs with very good connectivity properties. Okay? So it's also a very nice story behind Margulis's construction of expander graphs. And the thing, and the way it is that Margulis at the time was working in in the Soviet Union, and he faced significant problems on account of his being Jewish in the Soviet Union. For instance, he wasn't allowed to go to Helsinki to pick up the Fields Medal. So one of the, the way it works is that he was, even though he won the Fields Medal and so on, he was asked to work at an institute for information transmission. So there's some kind of telecommunications institute. And over there, his boss posed the problem to him and said, look, why don't you try your hand at this? And Margulis immediately found a beautiful way of solving it. Okay, so this is the construction of expanded graphs. And then Margulis is also known for revolutionizing the world of metric Diophantine approximation. So these are some long-standing conjectures of Diophantine approximation called the Baker-Springer conjectures. I don't think I'll have time to talk about it, but I'll briefly mention it later. And then he's known for, various other things, each of which could merit a separate talk. There's the normal subgroup theorem, there's the Margulis lemma in hyperbolic geometry, there's the Bowen-Margulis measure, there's random walks on homogeneous spaces. I also, one should mention Margulis's thesis, which was a beautiful result on counting closed geodesics. And indeed, one should also mention Firstenberg's thesis, which gave rise to the famous Firstenberg boundary for a semisimple Lie group. So as you can see, these two eminent mathematicians have really spent a lifetime proving extremely beautiful results. So let's try to get a sense of the kind of objects they work with. And in order to do that, we need to formalize the notion of a dynamical system. So rather than provide a definition, I'm going to proceed by example. So the first example of our topological space is the torus. Okay, so it's a quotient of the real numbers by the integers. All right, and it admits many interesting maps. Okay, so for instance, a very interesting map on this is what I'm going to call the ×2 map on the torus. So this is a map which takes a real number x and multiplies it by 2. When you multiply a real number by 2, you get some other real number, and if you go mod 1, you get back a point on the torus. Okay, so it's a map from the torus to itself, which is multiplication by 2 mod 1. So this is, of course, seemingly a very simple example. And as we're going to see, it has a very rich structure in terms of a very rich mathematical structure. And we're going to learn quite a bit about this ×2 map. And we're also going to see that indeed, there are actually many questions that we can't answer, even about things like the ×2 map. So it's a very simple map to describe, and has a very rich mathematical structure, not all of which has been unraveled as of today by mankind. Another main example that I want to emphasize in today's talk is going to be a slightly non-abelian version of the torus. Okay, so as we saw, the torus is a quotient of the real line by the integers. And in our brief discussion on the arithmetic theorem, we brought up lattices in semisimple Lie groups. So here is a semisimple Lie group. This is the group of 2 by 2 matrices with determinant 1, okay, and real entries, and it's SL2R. And this has a nice lattice in it, which is the subgroup consisting of matrices with integer entries, okay? So when I mean a lattice, so this is a discrete subgroup, okay? That's the first thing. And the second thing is that this quotient that we formed here, this topological quotient, it has, so there's a there's a nice PAR measure. Okay, so it's a translation invariant measure, which one can put on SL2R. Okay, and so this measure descends to this quotient, and this measure is finite for the quotient. Okay? So the quotient of SL2R by SL2Z has a finite SL2R invariant measure. Right? So such a subgroup, such a discrete subgroup is called a lattice. Okay, so what it means is that this nice quotient over here forms a probability space. Okay, so you normalize the measure to have to give the space measure 1. You get a nice probability space. On this probability space, you have actions by subgroups of SL2R. Okay, this action is just by translation or by multiplication. Okay, so you take a matrix group, subgroup of SL2R, and you act on this quotient by left multiplication. Okay, so this is another class of very rich dynamical systems with extremely complicated behavior, and this is also one of the main examples of today's talk. So one example of this matrix group acting is what I call GT here, and this is the group of diagonal 2x2 matrices. Okay, so it's as T varies, this is a copy of the multiplicative reals acting on SL2R factor SL2Z. And what I'm going to try to draw out is some connections between the example that we saw previously, which is this ×2 map, and this example, and high dimensional versions of this example. So those of you who are familiar with some hyperbolic geometry would have immediately realized that, in fact, what I'm talking about here is the geodesic flow on the modular surface. So let me briefly recall this beautiful story. And so we know that the hyperbolic upper half plane admits an action of SL2R by Mobius transformations. And so this quotient SL2R factor SL2Z that we have over here can be viewed as the unit tangent bundle of the quotient of the upper half plane by SL2Z, which is otherwise known as the modular surface. So you should think of it as, it's a finite volume, non-compact hyperbolic surface. Okay, and so you can go along geodesics with speed, unit speed, and that gives you a geodesic flow on this surface. And the geodesic flow on the surface under these identifications that I just discussed can be viewed as an algebraic action of this one parameter subgroup GT on the quotient SL2R factor SL2Z. Okay, so if you know the hyperbolic story, that's great. If you don't, it doesn't matter. All you have to do is remember that we are considering an action by left multiplication of subgroups of Lie groups on homogeneous spaces by lattice. Okay, that's the picture. Another striking example is provided by what is called the horocycle flow, which is what you get by moving along horocycles, which are sort of circles tangent to the boundary on the upper half plane with unit speed. So this was a diagonal matrix, as you can see, is an upper triangular matrix. Okay, so it's a copy of the additive real. And
Anish,
yes?
One question came, it says quotient by PSL2 or SL2?
Yeah, so that's true. If I, yeah, so when you look at action on the upper half plane, it should be, it's better to look at PSL2, but that's just trying to show some, I'm okay with SL2. That's, is that okay?
Carry on, yeah, no problem, just carry on. Yeah.
Oh.
Please carry on.
Yeah, so it's a good question. So usually when you talk about Mobius transformations, people talk about the projective special linear group. So you go modular center, but for us, it doesn't matter so much. Okay, very good. So these are the kind of dynamical systems that we are going to study. And for a person who studies these things, the basic questions are, okay, can you classify in some meaningful way these dynamical systems? Can you provide explicit descriptions of periodic points or invariant sets? How about providing a list of ergodic invariant measures? So I'll define all these notions in the talk, and then we'll see what we can say about each of these. So here's a picture taken from Wikipedia of the fundamental domain for the modular surface in the upper half plane. So this is the shaded part here. It's just a fundamental domain. So like the fundamental domain for the circle is the unit interval, and for the for the torus is the square, and so on. This is a good fundamental domain for the modular surface. It's the triangle with one vertex to infinity, and it has finite volume. All right, so this is just a picture. All right, so now we are going to go back to the multiplication by 2 map, or more generally the multiplication by p map, which I remind you is x going to px mod 1. Okay, and what can we say about this map? So first, let's define the notion of what it means to be invariant under the map. So a subset of the torus is said to be invariant under times p if the image of the set under times p lands inside the set. Okay, so essentially this map does nothing to the set. Okay, so an invariant set is unmoved by the map. And so one would like to know, well, are there invariant sets for these maps? What do they look like? How many are there? Can you write them down? So on and so forth. So as it turns out, there are many invariant closed subsets for times p. All right, so there's a reason for this, which I'll come to. And what are examples of this? So there are many examples. Of course, the trivial example is that the circle itself is invariant. Less trivial example is obtained if you take times 3, and it turns out that the middle third Cantor set on the unit interval turns out to be invariant for times 3. Okay, so it's a closed, totally disconnected set, and it turns out to be invariant for times 3. As we'll see shortly, this is not a coincidence. The point here is that this times p is more or less, morally speaking, what one calls a Bernoulli shift. Okay, and it's well known that these have a lot of invariant sets. So any subshift of this Bernoulli shift gives an invariant Cantor set. Okay, so let's see how one could view times p in this manner, and it's very easy. So what one does is recalls that every real number has a base p expansion. And what times p does, so the base p expansion is given in this form. It's unique except if the number is rational, and rational numbers have 2 expansions. And its number is rational if and only if the base p expansion is eventually periodic. Okay. So what times p does is it takes the base p expansion of a number and shifts it by 1. Okay, so if you take a real number and its base p expansion is 0.x1, x2, and so on, apply times p, you shift it by 1, right? So it's basically a shift map. Times p is morally a shift map. Shift maps and their associated dynamics are extensively studied. They're some of the most well-studied examples of dynamical systems. And so this is one of the reasons why we have a lot of information about times 2, okay? So to summarize, there are plenty of invariant subsets for each map, times 2, times 3, and so on and so forth. But one can ask the natural question, are there lots of joint ones? Okay. So what does this mean? This means that I'm asking the following question. Do expansions in base 2 of a number and expansion in base 3 of a number have anything in common? It is a very perfectly reasonable question. In other words, or put another way, if I have closed invariant subsets under times 2 and times 3, respectively, do they share any common structure? Okay, so this is a very natural question, and as we'll see, it's a very rich question as well. So let's mention some positive results in this regard. And to do so, we defined the notion of multiplicatively independent integers. So two integers p and q are multiplicatively independent if log p over log q is not a rational number, okay? Or equivalently, if they're not both rational powers of a single integer, okay? So that's what it is. So 2 and 3 are multiplicatively independent, so are 2 and 6. So GCD PQ equal to 1 is not necessary. And 4 and 8 are examples of numbers which are not multiplicative. Okay. All right. So given two multiplicatively independent integers, I'm going to form a semigroup which consists of taking powers of p and q. Okay. So this is consists of all numbers and vary over the natural numbers. All right. So it's a semi in basically we know a lot classically about these Bernoulli shifts. Now we move on slightly more complicated questions. As I look at two and something. So what we're taking by 2 and 3 and on the understand.
Anish,
that's what's happening.
Anish, Anish, sorry to interrupt you. Can you turn your video off? We can't quite hear you clearly sometimes.
Okay. Turn the video off?
Yeah, your video off. Yeah, go ahead.
Okay. The video off?
Yeah.
Okay. Actually, Q, which is a semi-group generated by, so here's a beautiful result of Firstenberg from 1967. And it says that if you be multiplicatively independent and look at subset under this action of this has a very, it has to be either the torus or it has to be finite, necessarily a subgroup of the rational numbers. Okay? So it's a very striking result. It's a topological rigidity result. It says that individually the maps times P and times Q have enormous multitude of closed invariant subsets. Together, they are very, very few. So in a sense, the dynamics, the maps times P and the times Q, where P and Q are multiplicatively independent, are really very different and don't see anything of each other. Okay? So this is a very famous theorem of Firstenberg. So this has a very nice Diophantine consequence, which I would like to mention now. And this Diophantine consequence is that if you take an irrational number and look at the orbit obtained by starting with a semigroup as before, namely a semigroup generated over the orbit get by looking, so you look at it of the in causation theorem, which is that if alpha is irrational, then n times alpha is in circle as n is over the number. So this is a more delicate statement where instead of varying over the natural number, we're varying over smaller semi-group, the natural number is a subset of torus. Okay. Okay, to speed up a little bit. So one of the main ideas introduced by Furstenberg in this paper is the notion of disjoint. It's formal description. So a nice group, some nice low group acts continuously and y. Adjoining of x and y fit with these groups with a group action of G, closed subset of period
Anish,
projection or subset plus
Anish,
yes?
Just a minute. Your voice is breaking up. I'm not sure why. So anyway, the break is coming in 5 minutes, and you can start
maybe
again.
Should I take a break, or I can just move closer to?
Yeah, go ahead. Yeah. Do that, and then we can take. Yeah, we'll take a break.
Is that better?
Yeah, it's a little better.
Okay, so all right. Can you hear me now?
Yeah, it's better now. Yeah, carry on.
Yeah. Okay. All right. So I'm going to speak as close to the microphone. All right. So adjoining is a closed subset of Cartesian product of x and y invariant and the diagonal action of G, whose projection to the first coordinate x and the second coordinate is y. Right. So two systems. So two dynamical systems using G acting on x and G acting on it. If the only joining is the trivial joining, which is the product. Okay, so Firstenberg introduced this really fundamental notion of disjointness in this while studying this ×2 and ×3 problem of torus, and this notion has the enormous show in dynamical systems over the years. All right, so now move on to measure theoretic rigidity. So far, we saw a beautiful result of Firstenberg, which was a topological result. It said that closed invariant sets have a particular structure. So now let's try to see what that would mean in the measure theoretic on which a semigroup G acts is said to be invariant if for every G in G, we have that the measure of G inverse A is the measure of A, all right? So A isn't the subset, the measurable subset A is not moved around by G. And now we come to a fundamental notion, namely that of ergodic measures. An invariant measure is said to be ergodic if for every A which is invariant under every little G in G. So if, so I have a group acting or a semigroup acting on a space. And so I have an action by every element in the group. So if I have a subset of the space which is invariant under every G in G, then this must satisfy that it's negligible as far as measure is concerned. So it's either measure 0 or has a complement, or its complement has measure 0. Okay? So as far as the measure is concerned, this notion doesn't really capture it, right? So ergodic, an invariant measure is ergodic if from a measurable point of view, it's negligible. It's not very interesting. And so one could ask, well, is there a measure theoretic version of Firstenberg result? And the answer is actually there isn't. So here's a famous conjecture of Firstenberg from 1967 from the same paper in which he proved his result. And it says that let P and Q be two multiplicatively independent positive integers as before. Any Borel measure mu on T, which is ergodic under the action of the semigroup SPQ, has only two options. It's either the Lebesgue measure or an atomic measure supported on finitely many rational points. So this, I take you back to the topological theorem where it said that closed invariant sets have to be either everything or finitely many rational points. The measure theoretic version says that any ergodic invariant measure has to either be everything, namely Lebesgue measure, or be supported on finitely many rational points. So it's more or less the exact analog of the topological result on the measure theoretic side. And this is basically the most famous open problem in ergodic theory. So as I said in the beginning, there are things about multiplication by 2 and multiplication by 3, which are just wide open and we have no idea how to go about solving it. All right. So this is the paper in question where Firstenberg introduced disjointness and proved his famous result and also stated his famous conjecture. So I'm really a little bit short on time. So I'm going to skip this part. So I wanted to mention a beautiful result of Rudolph on positive entropy, but I don't think I should because I need to say a little bit about Semereti's theorem. So basically, I just want to leave this message with this in this section, which is that the dynamics of times P and times Q do not share any common structure, both topological or measure theoretic, unless there is an explicit, obvious algebraic reason for them to do so. This theme is going to recur again and again in my talk in various different examples. All right, so in the last few minutes, I will present to you quickly Firstenberg's landmark work on ergodic Ramsey theory. So I'm sorry for skipping a few slides, but I really am running out of time. So let's recall van der Waarden's famous theorem from 1937 in ergodic Ramsey theory, which says that if you color the integers using C colors, then for every integer k, there is a monochromatic k-term arithmetic progression, all right? So this was basically studied subsequently by many people, including Roth and Erdos and Turan. Erdos and Turan conjectured that this sort of, the main thing that you're looking at here in this coloring is existence of one of these subsets of colors with positive Banach density. Okay, so they conjectured, and this was proved by Semereti in 1974, that any subset of the integers with positive upper density contains arbitrarily long arithmetic progressions, and upper density, as we all know, is just defined as follows. The it samples intersections of your subset A with bigger and bigger intervals centered at 0. Okay, so this is a very, very important result of Semereti. And this result and van der Waarden's result also admits finitary versions. So these are the finitary versions of van der Waarden and of Semereti. So I'm just going to skip to Semereti. It says that if k is a positive integer and delta is positive, then there exists an n depending on k and delta. It says that any subset of 1 through n of size at least delta n contains an arithmetic progression of length k. All right. So it's a very striking result. Firstenberg gave a completely different proof of Semereti's theorem. And I want to very, very briefly indicate how this goes. So the idea is to translate the problem into dynamics by what is called the Firstenberg correspondence principle. It's a very influential piece of work. So the dynamical system to consider now is basically sequences, 0-1 valued sequences, along with the shift map, right? So the shift map just takes a sequence xn and shifts it, right? So this is a dynamical system, and it's possible to connect this ergodic Ramsey theory, similarity type theorems to explicit recurrence statements on such a space. So you equip the space with the product topology, and this is a compact space. So Firstenberg's proof proceeded using a famous result, which essentially is called measure theoretic multiple recurrence. Okay, so in the beginning of the slide, I have a topological version of this recurrence, which is an easier statement, and which actually is equivalent to van der Waals theorem, which we stated. But let me focus on Firstenberg's result, which was measure theoretic multiple recurrence. So you take a measure preserving system, so a probability space and a nice map and a positive integer k. Then for any measurable subset of x with positive measure, you can find an integer n, such that when you look at the intersection of E with iterates of T of, so you take E and move it around using your dynamical system T, and then you take, so K of these and intersect them. And so Firstenberg guarantees you that the measure of the intersection is still positive. So this turns out to imply Semireddi's theorem, and this actually opened up a really huge new subject in its own right, and leading to work of, among others, Gowers, Green and Tao, and so on and so forth. It's still very active. All right, so I think I ran out of time, so I'll stop now and open up for questions.
Okay, thanks, Anish. People can use the hand raise feature and can raise your hand. I'll unmute you. You can ask questions to Anish. Okay, Naveen has a question. I'll unmute Naveen. Go ahead. Yeah. Naveen, can you ask?
Am I audible or?
Yes.
Yeah. Yes,
okay. Yeah. So thanks for this wonderful talk. So I mean, I vaguely recollect that again, this is from 20 years back. I suppose that I was reading all of this. Is it not true that like the Firstenberg correspondence principle and such like transference principles between number theoretic statement and ergodic theory or topological statement, they rely upon the axiom of choice in some way?
No, so it's true that Firstenberg's original argument relied on the axiom of choice, but I think this now removed. Yeah, so it's true, what you're saying is true that Firstenberg's first argument relied on the axiom of choice, but now that dependence has been removed. So for example, there's a work of Terry Tao where he uses ideas from Gowers' work to actually provide an explicit bound for nk delta in using Firstenberg's method. So now there's no dependence on the axiom of choice, and it's even explicit.
Are there any other questions? Anybody else? Okay. I'll wait for a minute. Yeah. Okay, so then what we'll do is we'll take a 10-minute break. I'll leave the room open. I'll unmute you all. You can talk to Anish if you want to talk to Anish, or he may take a break. But I'll come back at 3:25.
Okay, I'm around, so I'm happy to answer more.
Yeah. Go ahead.
Can you go back to, this is Parthenic, by the way, and it's very nice talk.
Thanks, okay.
Only thing is the last proof, you went a bit too fast. Can you just go over it once more? And I was also not paying attention for that, sorry.
Okay, so one second.
So Anish, I'll be back at 3:25.
Okay, okay, sure. Okay. So which one? Partner, which one?
This proof, yeah.
Yeah, so I didn't actually prove anything. So basically,
I mean, how does it work? The idea, yeah.
Yeah, so basically, yeah, so basically, it's kind of so the first thing to see is that there's some kind of open cover topological multiple recurrence. So we all know like the Poincaré recurrence theorem, right? So basically, it's quite easy to see that if you look at van der Waals theorem about this coloring in the integers. So the finitary version of van der Waals theorem, where you take this k and r positive integers and find the positive integer m such that any partition of 1 through m contains an arithmetic progression of length k. So this is essentially more or less, so it's exactly this kind of open cover topological recurrence theorem. Right? So basically, you can probably, I mean, if you think about it for a second, it's basically all you're asking for is taking k iterates of your shift map and trying to see if you have some meaningful intersection. And so Firstenberg's Firstenberg's main insight was somehow that there's also a lot of things can be extracted from kind of a measure theoretic open cover recurrence.
I have a question, Anish.
Yes. Okay.
So this open cover recurrence theorem, isn't this for only for compact metric spaces?
Yeah. So I'm basically I'm going to apply it to this shift space, which is compact.
It's compact, right? This space is compact.
Yeah. So I'm applying it to shift space, which is compact.
And it seems completely false for non-compact spaces, because even if I take it just the obvious open cover of Z just by singletons, there it seems to be false.
Yeah. So I'm taking a complex.
Okay.
Yeah. So maybe since I have a few minutes, I can just, if you don't mind, maybe go to the slides which I skipped. So basically,
Sure.
Basically, nice. What happened is that so we have this a famous conjecture of Firstenberg called the times 2 times 3 conjecture, and it's still not known whether you can completely classify ergodic invariant measures under times 2 and times 3. But actually, we do know quite some, we have some information, and this is a beautiful result of Dan Rudolph. It says that, you can take the same maps, the same setting, the same semi-group SPQ. If you make one further assumption on the ergodic invariant measure, namely that under one of these maps, say times P, this measure has positive entropy. So I'm not telling you what that is, but it's a condition, it's some kind of condition. Under this condition, you can actually say that the measure is indeed Lebesgue measure. Okay, so it's not everything, but it's a major it's a very, very important result in its own regard. And the reason why it's a natural statement is because if you take measures supported, Dirac measures supported in periodic orbits, then they have zero entropy. So that's why this condition is a condition which makes sense But of course, there are non-atomic invariant measures which can also have zero entropy. Right? So this result of Rudolph has an analog in the non-abelian world, which I will try to mention towards the end of this talk. So I thought I should mention Rudolph's results. Okay.
Thank you.
Yes.
So Dan Rudolph was his student, right? Firstenberg's student. Was he?
I'm not sure, actually. I don't know. I'm embarrassed to say I don't know.
Most probably.
Firstenberg moved to Israel early on, after a few years in the US. So
Okay.
I don't know. The honest answer is I don't know.
Okay.
Okay, good. So let's take a 2-minute break.
I'm back, Anish. I'll wait 2 minutes.
Okay.
He was Ornstein's student, Anish.
Who's student?
Ornstein.
Oh, I see.
Stefan Ornstein, that Ornstein. Yeah, Ornstein. I just checked in Wikipedia.
Anish, you talked about these positive entropy and Lebesgue measure. Can you tell me something more? Like, are there any non-atomic measure known which is not Lebesgue measure and it's invariant under these 2 and 3?
Yeah. There are lots of examples.
Okay, so they're not classified, is it? Or what?
No, it's kind of it's the situation is kind of okay. So basically, I mean, the situation is so there's so if you take the geodesic flow on the modular surface, then there are lots and lots and lots of invariant measures, and it's impossible to classify. And this is similar to the ×2 situation.
Okay.
But then what happens is that if you take a high rank action, like if you take an action of R2 on SL3 R factor SL3Z, then the situation is very similar to Rudolph's situation. So if you have positive entropy, then you have a classification, but conjecturally, you should have a classification without any positive.
Okay.
So basically, the situation is that, so essentially we are more or less after Rudolph and 1 or 2 other works in that direction, we seem to be stuck with this positive entropy condition. Some really new idea needs to come along to remove it, and then one can move first.
Thanks. The talk is going very well. Thank you.
I'll just mute everybody again and then start again. Give me a second. Anish, can you unmute yourself?
Yes. Can you hear me now?
Yes, I can hear you. Okay. Okay. Yeah, go ahead. Will you get second talk?
Okay, great. So in the first talk, in the first part of the talk, we saw some examples of dynamical systems, a beautiful result of Firstenbergs, and some connections of dynamical systems to number theory. In the second half, I'm going to concentrate on the work of Margulis, and we're going to continue on the same theme. Okay, so I remind you from the first half that at the very beginning, we saw some examples of dynamical systems. One of them was ×2, and the second one was left multiplication by diagonal matrices on the quotient of SL2R by SL2Z. And the third one was left multiplication by the upper triangular group on the quotient SL2R factor SL2Z. So in the first half of the talk, we saw some results about ×2. The second half is going to focus on dynamics motivated by the latter two examples. Okay, so in order to do so, I'll start with the subject of quadratic forms. And we are going to try to understand values of quadratic forms, okay? So this is a famous theorem of Meyer. I'll just remind you that if I take a quadratic form, a rational quadratic, indefinite quadratic form in at least 5 variables, then this indefinite quadratic form has a non-trivial integer solution, okay? So this is a very classical theorem. It's a consequence of the local to global principle. And it can be found in Sayre's book on arithmetic, for example, okay? So what it means is that if I take a quadratic equation with rational coefficients and it's indefinite in at least 5 variables, then I can solve this equation in integer, all right? So I can solve this rational quadratic equation in integers. That's what this theorem says. And as I said, this is a consequence of the Hasse-Minkowski local global principle. So Oppenheim, who was a British mathematician, around the year 1929, asked himself, all right, so what if I take a quadratic form which is not a rational quadratic form, okay? So according to Meyer's theorem, a rational quadratic form gives you an equation which can be solved in integers. So Oppenheim made the guess that if I take a form without rational coefficients, then maybe I can't solve this equation in integers, but perhaps I can get as close to 0 in integers as possible, okay? So here's a stronger statement which came to be known as Oppenheim's conjecture. And it says that if Q is an irrational quadratic form, so by this I mean that Q is not of the form real number times a form with integer coefficients, okay? So a form which is not a real number times a form with integer coefficients is going to be called an irrational quadratic form. If Q is indefinite, which means it takes both positive and negative values, and if Q is non-degenerate, so roughly speaking, this means that I can't somehow reduce questions about Q to questions about a quadratic form in a fewer number of variables, and Q has at least 3 variables, then the set of integer values taken by Q is dense in the real line, okay? In particular, I can solve the inequality Qx less than epsilon, where x is now an integer vector, okay? So this is an analogy with Meyer's theorem. Meyer's theorem said you can solve Q of x equal to 0 for a rational quadratic form, and x can be taken to be an integer. For irrational forms, the analog is that you can solve the inequality Qx less than epsilon. In fact, not only can you do that, the set of values taken by Q on integer points is dense in the real line, okay? So this was a conjecture made around 1929, and this was open for many, many years. It attracted a lot of attention among the analytic number theorists, especially those who specialized in the circle method. And around the, so here's an example of a irrational, indefinite, non-degenerate quadratic form in 3 variables. Okay, so this is what you should keep in mind. And so, as I was saying, this conjecture, it's a straightforward number theory conjecture, and it attracted a lot of attention by number theorists, and they were successful in proving special cases. So, if I recall correctly, if we move forward from 1929 to the late 1970s, then this conjecture was known for certain diagonal forms in at least 21 variables. Okay, that was the status. And then things took rather dramatic turn. So in order to describe this dramatic turn, let me recall the space of lattices. Okay, so as we discussed in part 1 of our talk, SLNZ is a lattice in SLNR. So we saw SL2 in the first talk, but that actually, whatever I said about SL2 holds for SLN, which means that the quotient of SLNR by SLNZ carries a finite SLNR invariant probability measure. So one important thing about SLNR factor SLNZ is that you can identify it with the space of unimodular lattices in Rn. So these are lattices in Rn with covolume 1. And SLNR, of course, has a natural action on these lattices. And you can easily check that this action is transitive, and moreover, that the stabilizer of the lattice Zn is SLNZ. Therefore, you can identify the space SLNR factor SLNZ with the space of unimodular lattices in Rn. And as we discussed in part 1, a subgroup of SLNR acts on this space by translation, and this gives a very rich dynamical system. Okay. So as I said, Oppenheim's conjecture was completely in the realm of number theory till a point in the late 70s when M.S. Raghunathan made the striking observation that, in fact, Oppenheim's conjecture follows from a statement entirely about the dynamics of subgroup actions on homogeneous spaces. All right. So he made the following conjecture. He said that Oppenheim's conjecture follows from the following statement, namely that any orbit, so I start with this quadratic form Q, and with the quadratic form Q comes attached a natural subgroup, and this natural subgroup is a special orthogonal group of the quadratic form Q. It's a subgroup of SL3R, which leaves the quadratic form invariant. Okay, so it's a nice orthogonal group, and it's a subgroup of SL3R, and therefore it can act on the quotient SL3R factor SL3Z by translation. Okay. So Raghunathan made the striking observation that Oppenheim's conjecture follows from the following statement. Any orbit of SOQ acting on SL3R factor SL3Z is either closed and carries an SOQ invariant probability measure or is dense. Okay, so let's think about this for a second. This is a remarkable observation, and in fact, the statement is also quite remarkable. You see, this SOQ action on SL3R factor SL3Z, this is known to be an ergodic action. So it's a very chaotic action. And what Raghunathan says here is that Oppenheim's conjecture follows from a statement, and the statement predicts the behavior of every orbit of SOQ. Okay, so this is a striking thing. So what is being said here is that one can describe every orbit of SOQ acting on this quotient space. So those of us, I mean, you know, if you think about it for a second, this is a rather mind-blowing thing, right? So you start with some chaotic dynamical system, and then if you're very lucky, you hope to say something interesting about almost every point and so on and so forth. But here, and this is again an example of the rigidity we spoke about in the first part of the talk, we want a statement about every orbit, okay? Every orbit of SOQ acting on X. All right, so let me make some remarks on Oppenheim's conjecture. So it is relatively easy to see that Oppenheim's conjecture can be reduced to 3 variables. And this important thing which Raghunathan realized is that the orthogonal group of quadratic form, which is indefinite in 3 variables, is generated by unipotent 1-parameter subgroups. So remember that for the first part of the talk, we had these upper triangular matrices. And a key feature of the orthogonal group of the quadratic form that we're looking at is that this orthogonal group is more or less, morally speaking, SL to R. Okay, so it's more or less SL to R. And it's actually crucially generated by unipotent 1-parameter subgroups. So it's generated by these upper triangular guys. This is very important fact, and it underpins the Raghunathan's reduction of Oppenheim's conjecture to dynamics of these orthogonal groups. We will see more in a second. So having translated Oppenheim's conjecture into a dynamical form, Raghunathan went on to conjecture a very general topological rigidity statements for actions of unipotent subgroups on homogeneous spaces of D groups. So these are landmark conjectures of Raghunathan, called the Raghunathan conjecture. And Margulis proved an instance of the Raghunathan conjectures for the special orthogonal group acting on SL3R factor SL3Z, thereby proving Oppenheim's conjecture. Okay, so it's really a very beautiful story. So there's a long-standing conjecture, and suddenly a striking observation converts it to a completely dynamical statement, and then this dynamical statement is resolved. All right, that's the story. So subsequent to Raghunathan formulating his very general conjectures for topological rigidity of unipotent flows on homogeneous spaces, S.G. Dani made measured theoretic versions of these conjectures. And subsequently, in the 80s, there was a lot of activity in this area, and there was striking progress by Dani and Margulis, and finally in the early 90s, the conjectures of Raghunathan and Dani were comprehensively settled by Marina Ratner in landmark work. Okay, so I'd like to point out the similarity to part 1 of the talks. Part 1 of the talk started with ×2 and then added ×3, and then we looked at topological rigidity for ×2, ×3, and measured theoretic rigidity for ×2, ×3. And here we have a non-abelian version where we take an orthogonal group acting on a homogeneous space, and we have a topological rigidity and a measured theoretic rigidity. Okay, so this theme underpins the work of both Firstenberg as well as Margulis. Okay, so let me try to indicate how Raghunathan reduced Oppenheim's conjecture to a dynamical statement. So this gives us some flavor of how to translate from dynamics to Diophantine analysis. And so what you do is you start with a quadratic form, x squared plus y squared minus z squared. So some of you might complain that, well, all this is fine, but this form that you've taken is not an irrational quadratic form, but that doesn't really matter so much. Okay, so let's just take the standard form. And the reason it doesn't matter so much is if I take an irrational quadratic form, then I can rewrite that irrational quadratic form as a scalar multiple of this quadratic form. So there I can find the matrix G in SL3R and a non-zero real number lambda such that my quadratic form is lambda times Q0 GV. Okay? All right. Moreover, the stabilizer of my quadratic form in Oppenheim conjecture is a conjugate of the stabilizer of the standard quadratic form, which was SO21. So it's G SO21 G inverse. Okay. All right. So let's set up some notation. So H is going to be my orthogonal group SO21. G is going to be SL3R and gamma is going to be SL3Z. All right. So here's what underpins Raghunathan's observation. So he noticed that you see this quotient of SL3R by the orthogonal group SO21 more or less is the moduli space of quadratic forms that we want to consider. All right. And this moduli space of quadratic forms that we want to consider admits an action of gamma on the right. All right. And so you can deduce results about density of values for quadratic forms by a careful analysis of the gamma action on the space of quadratic forms. So let me show you how it works precisely. So what you do is you look at the dual picture, all right? So you look at the action of H, which is an orthogonal group generated by unipotent elements on the quotient space G mod gamma, all right? So if I consider this action of H on G mod gamma, remember, let me recall to you from the last slide that I started with some fixed standard quadratic form, and I have a different quadratic form in my theorem. And this quadratic form is related to my standard quadratic form via a matrix in SL3R called little g. Okay, this little g, when I look at the coset little g gamma, I get a point on my space G mod gamma. Okay, and I'm going to look at the orbit of this point G gamma under the action of my orthogonal group. All right. And so Raghunathan said that there should be only two alternatives, namely either this orbit should be dense or it should be closed and have a finite invariant measure. All right. So it should be essentially either a periodic orbit or a dense orbit. Okay. Only two alternatives. So let's analyze what happens if the orbit is dense. So if the orbit is dense in G, then the set of values, integer values taken by the quadratic form, which is the same as the set of values taken on the lattice GZ3 by my standard quadratic form. And since my subgroup gamma SLNZ stable SL3Z stabilizes Z3, this is the same as Q0 of G gamma Z3, right? This is the same because H is the stabilizer of the quadratic form Q0 as Q0 of HG gamma Z3, but HG gamma is assumed to be dense in G, and therefore this is just the set of values taken by Q0 on GZ3, which we know to be just the real numbers, okay? So if HG gamma is dense in G, then indeed the quadratic form takes a dense set of values on the integer lattice, all right? So this is one part of the dichotomy predicted by Raghunathan. On the other hand, it is possible that the Hg gamma orbit is closed and has an SOQ invariant probability measure. Okay, so what happens in this case? In this case, what happens is that it's not very hard to check that in this case, in fact, if you intersect gamma with GAG inverse, then this is a lattice in GAG inverse. So GAG inverse, I remind you, is it's a stabilizer of the quadratic form that I have. Okay, so I find a lattice in the stabilizer of my quadratic form, and there's a theorem called the Borel density theorem, and according to this Borel density theorem, I would get the implication that in fact the stabilizer of my quadratic form is contained in the Zariski closure of this lattice. Okay, so that's how it is. That's a direct application of Borel density theorem, and what this means is that in fact, because SOQ is contained in the Zariski closure of this lattice, it has no choice but to be defined over Q as an algebraic group. So you know that an algebraic group is also a variety, and so it has some defining equations, and so in particular the defining equations of this algebraic so this algebraic group has defining equations over the rational numbers. Okay, but this is only possible if the quadratic form that I started out with is actually a rational quadratic form, but this is a contradiction. So that's how Raghunathan's observation connecting Oppenheim's conjecture to the dynamics of the SOQ action on G mod gamma goes. So as I mentioned, in fact, after Raghunathan made his observation, Margulis proved the dynamical statement, thereby settling Oppenheim's conjecture. So this problem of quadratic forms is one of Margulis's favorite problems. So he has returned to it time and again after proving Oppenheim's conjecture. And soon after, Dani and Margulis actually studied a very natural version improvement of Oppenheim's conjecture. So instead of asking just for density, one could ask a more quantitative statement, and it says that, okay, what if I look at integer vectors in a large ball in Rn and ask how many of these have the property that when I plug it into the quadratic form, it lands in some interval, say between A and B. Okay, so I fix some interval AB, and I take larger and larger balls in Euclidean space, and I want to ask how many lattice points are there in these balls, which have the property that when I plug the lattice point into the quadratic form, I land between A and B. So this is seen as a very natural quantitative improvement of Oppenheim's conjecture. And so the result is as follows. So you can take indefinite irrational quadratic form like in Oppenheim's conjecture in at least 3 variables. Then in fact, you have a lower bound for the number of such solutions, and it's the right lower bound. So basically, it turns out that the solutions, it turns out that the integer points or lattice points which have this property are distributed in some kind of uniform manner. And so the number of such lattice points turns out to be the volume of this region. So the lower bound is what is known in at least 3 variables, and if you can move to 5 or more variables, then you have an exact limit. Okay, so this lower bound is a famous result of Dani and Margulis, and the upper bound is a famous result of Eskin, Margulis, and Moses. So in fact, there's also some upper bounds for 3 and 4 variables, but they're somehow more complicated. So it's not, the asymptotics are not as clean, so I didn't state them. So the methods involved in this result are also kind of, so in Dani Margulis' paper, the methods that were invented and used have also become mainstays in dynamical systems over the years, and really play a fundamental role in latter discoveries, including the work of many people like Lindenstrauss and others. And similarly, work of Eskin, Margulis, and Moses also introduced some really fundamental new ideas, which played quite a serious role in the work of Benoit and Kant on classification of stationary measures for actions of unipotent groups, and in turn somehow that played a crucial role in the philosophy of Benoit and Kant, played a crucial role in the work of Eskin and Mirzakhani on the classification of on the dynamics of SL2R action on Teichmüller space. So this kind of question somehow starts off with some innocuous looking quadratic form, but then it had like a really huge influence on very diverse parts of mathematics. Okay, so that's the part about quadratic forms, and now maybe I will go to another beautiful result of Margulis. So as I mentioned earlier, this space, the Gaussian space, SLN-R factor SLN-Z can be naturally identified with the space of unimodular lattices in Rn. And so, let me state a very well-known result describing the geometry at infinity of this space. So for a positive number, a real number epsilon, I'm going to denote by xn of epsilon to be the subset of lattices in Rn, unimodular lattices in Rn, whose shortest non-zero vector has norm at least epsilon, okay? So you take a lattice in Rn whose fundamental domain has area 1. You take its shortest non-zero vector and measure its length. If it's at least epsilon, it belongs to your set, okay? That's it. So by Mahler's compactness criteria, the set xn epsilon is compact, and in fact, so the sets xn epsilon provide an exhaustion of the moduli space of lattices by compact sets, right? So it's this is very easy to visualize, because the thing is that if since I've demanded that my lattices are all unimodular, the area of the fundamental parallelepiped of the lattice has to be 1. And so I can't have really very long vectors without having very short vectors as well. So if I don't allow my subset of lattices to have short vectors, then I'm going to get a compact subset of lattices. So that's the philosophy behind this result. And so here's a very fundamental result of Margulis. And it says that if I take the following dynamical system, I take a unipotent 1-parameter subgroup of SLN-R. So I ask you to cast your mind back to slide number 3 of the first part of the talk, where we saw the upper triangular matrices acting on SL2R factor SL2Z. So that's the example to keep in mind. So Margulis says that these upper triangular matrices have a fundamental property, namely that their orbits don't diverge. In other words, there exists an epsilon positive such that the set of X's in R for which UX lambda, so lambda is a lattice, it belongs to this compact set X and epsilon is unbounded, okay? So the orbit, so this is, I remind you, this is a non-compact space. And you have an ergodic action on a non-compact space. And the striking result of Margulis is that nevertheless, orbits of this action are going to come back to compact sets infinitely often. All right. So this is a very striking result. And in fact, this result was conjectured by Piatetsky-Shapiro and was used by Margulis in his proof of the arithmeticity theorem. It's a very beautiful elementary argument that Margulis provided. So it's very easy to prove this result for the SL to R factor SL to Z case with upper triangular matrices. It's much more difficult to prove it in higher dimension, but Margulis invented a really ingenious combinatorial argument to prove it. So this is another result of Margulis, which I think has a very long shadow. So it casts a long, it has been used in various forms in many, many impressive results. So for instance, after Margulis proved this result, Dani proved a very influential quantitative version of Margulis' theorem. And there have been further quantitative improvements, most notably by Kleinbach and Margulis, who used their quantitative improvement of Margulis's. So the chronology is that Margulis's theorem tells you that the orbit spends an unbounded amount of time in a compact set, but then you want to know more about, how big is the compact set and so on and so forth. And so these results were proved by Dani. And Kleinbach and Margulis made a further improvement on Dani's results, and they used it to prove a very influential, long-standing open problem in Diophantine approximation known as the Baker-Sprinjuk conjecture. So I won't have time to formally state this conjecture, but let me try to give you a sense of what it means. So, in number theory, it's very, very difficult to provide useful information about properties of particular numbers, okay? So this is very difficult, but what is less difficult is to provide information about properties which are common for, say, almost every number. Okay, so there are many properties which are enjoyed by almost every real number. So one such property is that almost every real number is not very well approximated by rational numbers, okay? So all real numbers enjoy some degree of approximation by rational numbers, but if you try to improve this rate beyond a point, you won't succeed, and almost every real number will not enjoy this property. So this is just a classical fact, and the Baker-Sprinjuk conjecture is an influential conjecture which states that if you take a reasonably smooth manifold satisfying some natural curvature conditions, then this almost every point on this smooth manifold also inherits the property of Euclidean space. So in other words, if almost every point in Euclidean space enjoys a certain Diophantine property, then that property is robust enough to be inherited by a strictly lower dimensional smooth manifold. Okay, so this was proved using a further improvement of Dani's improvement of Margulis' theorem. And then Kleinbach, Lindenstrauss, and Weiss actually made a still further improvement and made changes so that one could treat not just smooth manifolds, but also things like the middle third Cantor step. So this was also a big advance. And finally, I'd like to say that Margulis' non-divergence theorem for unipotent flows found another, so Eskin and Margulis wrote a very influential paper on the recurrence of random walks on homogeneous spaces. And this used very similar ideas to Margulis' theorem, Margulis' non-divergence theorem, and also borrowed philosophy of the Eskin-Margulis-Moses result on quantitative Oppenheim conjecture, which I mentioned some time ago. So Eskin and Margulis' result was very, work on random walks was quite influential, and that's what kick-started the work of Benoit and Kant, who answered a conjecture of Eskin and Margulis. So I don't have the time, but I think I should mention briefly. I didn't have time to discuss, I would have really liked to, a recent work on stationary measures and their classification, both on the torus and on homogeneous spaces. So this has been a beautiful story. So the two parts of the talk that I gave today, namely rigidity on the torus and rigidity on homogeneous spaces, recently there have been beautiful improvements on the classification, on stationary measures in both settings. So I don't have time for this, but you can look up the work of Benoit and Kant, and also the work of Fuhrmann, Moses, Burgan, Fuhrmann, Lindenstrauss, and Moses on the torus. So these are very beautiful works. So finally, I'd like to tie together the two halves of the talk that I've been giving. So in the first half, we saw times 2 and times 3, and we saw that times 2 and times 3 individually have extremely rich behavior, and together have very rigid topological behavior and conjecturally very rigid measure theoretic behavior. So on the homogeneous side, the analog is the geodesic flow, namely the diagonal action. So the diagonal action, if I take one diagonal matrix, if I take the thing that the matrix that we saw in part 1 of the talk, which was the diagonal matrix e to the t, e to the minus t, then this matrix this subgroup behaves a lot like the times 2 map on the torus, very rich behavior. And similarly to Firstenberg's principle about disjointness of times 2 times 3, there's a disjointness phenomena conjectured in the homogeneous world, namely the analog of SPQ that we saw in part 1 of the talk is an action of R2 given by the subgroup H, the diagonal subgroup e to the s, e to the t, e to the minus s minus t. So this is a nice action of R2 on the homogeneous space SL3R factor SL3Z. So you should think about this as the analog of SPQ in part 1 of the talk. And so there's an analog of the disjointness phenomena and also Firstenberg's conjecture. And this conjecture is conjecture by Margulis. Namely, it says that any compact H invariant subset of SL3R factor SL3Z is a union of compact H orbitals. Okay, so I would like to kind of point out that in Raghunathan's conjecture, we saw that it was really important that the acting group was generated by unipotent one parameter subgroups. Okay, so the way things have progressed is that we saw rigidity on the torus, and then we saw rigidity in homogeneous spaces for actions of unipotent subgroups and of subgroups generated by unipotent subgroups. This here is a completely different beast. It's not at all unipotent. It's the opposite end of the spectrum. Nevertheless, it is conjectured that in high rank, namely if I look at an R2 action, that in fact this R2 action should be topologically and measure theoretically rigid, okay? And this conjecture is still open, so this should be viewed as the analog of the Raghunathan and Dani conjectures, but for diagonal actions. This conjecture is still open. However, so before I say the however, it also has some striking number theoretic consequences. Namely, it would imply an old conjecture of Littlewood, who made this conjecture around 1930. And it says that if I take two numbers, alpha and beta, then the lim inf of n times n alpha and n beta. So this n alpha and beta is the distance to the nearest integer. So the product of this n times n alpha times n beta is 0. So the reason, so I'd like to remind you from elementary number theory that there are many numbers which are badly approximable by rational numbers, okay? So if alpha is such a badly approximable rational number, then the lim inf of n times n alpha is strictly positive. And we know that there are uncountably many such numbers. Littlewood's conjecture says that if I look at a number, a vector alpha beta, so a pair of numbers, then in some sense there are no simultaneously badly approximable numbers. None of them exist. This is a consequence of Margulis' conjecture. So you should view it as, just as in Firstenberg's measure theoretic conjecture, it's still open, times 2 times 3. But we saw that Rudolph, assuming a positive entropy on one of the actions, provided a measure classification. Similarly, in this non-abelian analog of Furstenberg's conjecture, Einsiedler, Katak, and Lindenstrauss made a positive entropy assumption on the acting group. And under this assumption, they proved that they couldn't prove Littlewood's conjecture, but they proved that the set of exceptions to Littlewood's conjecture has 0 Hausdorff dimension. Okay, this was part of Lindenstrauss's Fields Medal in 2010 in Hyderabad. And so with this, I'd like to end my talk. I hope I've been able to give you some sense of this beautiful subject and the enormity of the contribution made to it by Tristenberg and Margulis. Thank you.
Thank you very much, Anish. The one question by Parthenil, maybe I'll allow him to ask it first, and another question before that. Parthenil, do you want to ask a question? I'll allow you to unmute yourself 1 second.
Yeah, I can
unmute
unmute.
and ask the question.
Yeah, so Anish, Parthenil here. So in the instead of one parameter, if you have 2 parameter group, say, so in that case, you still have a duality in some form that you presented in the 1 parameter case. Sorry, can you hear me? Hello.
Can you hear me?
Yeah, can you hear me? This
Yeah,
yeah. So in the 2 parameter case,
can you hear me?
Yeah, I can hear you.
Yeah. Mm-hmm.
Yeah, so in the 2 parameter case, do you still have the duality that you talked about in the 1 parameter case? Like, you have
So
some...
the duality principle is a very robust and a reasonably general principle.
Oh, okay.
So it says that under various conditions, if you have a triple consisting of a Lie group, a subgroup, and a lattice, then you can say various things about the action of the lattice on the homogeneous variety of the Lie group by subgroup by studying the action of the subgroup on the space G mod gamma.
I see. I see.
This is like a general philosophy, and you can implement it to really spectacular effect in particular cases. Now, the issue at hand here is that the higher rank abelian action is fundamentally different, is conjectured to be fundamentally different from the rank 1 abelian action.
Okay.
So the geodesic flow is supposed to really be, it admits a symbolic description. It admits many closed invariant subsets and ergodic invariant measures, and it's not possible for us to classify all of them. And when you move to a high rank action, all of this is supposed to vanish, and you're supposed to have a clean rigidity statement reminiscent of Firstenberg and of Raghunathan Dani.
Okay. Thank you.
Mayuresh had a question. I'll ask him to unmute himself and ask the question, please.
So, can you hear me?
Yes.
So, during first half, you had mentioned this Firstenberg's conjecture on times P and times Q map.
Yes.
So, thing is it still a conjecture? Because last year there is a article published in Annals of Maths about this group of Firstenberg's conjecture by Meng Wu or something. So I will paste a link in chat.
That's true. So yeah, so that's a different Firstenberg conjecture.
Oh, I see.
That's also a very nice conjecture, and it was also, I think, solved independently by published Merkin. But it's a different conjecture. The times 2 times 3 is still open. So yeah, you should go for it.
Nice. Thank you.
Any other questions?
I had a question.
Yeah, go ahead.
Can you hear me?
Yes.
Okay. So in Raghunathan's formulation, we had that subgroups of SL2R acting on SLNR acting on SLNR by SLNZ. And this space can be thought of as the space of flat torus with volume 1.
Yes, that's right.
Would you ask similar questions for other manifolds? I mean, other volume 1.
That's a very good question. So, so there are 2 things you can do. So the first thing you can do is you can, as I mentioned already, so there's nothing very special about SL2R or SLNR. So the conjectures were made and proved for general semisimple Lie groups and lattice. So that's one thing you can do. But what Balarka is hinting at is another direction. And so you can view SL2R factor SL2Z as a moduli space of flat tori, and then you can ask, well, okay, so can one say something about moduli space of other geometric objects? And indeed, you can ask you can set up similar things for moduli space of higher genus objects, and actually it's much more interesting in some sense, and less is known about it. So in fact, the moduli space of flat surfaces admits an action of SL2R, and indeed, so an analog of kind of Raghunathan Dani conjectures for this action is the work of Eskin Mirzakhani.
Thanks.
Yeah. So the answer is indeed it can be formulated, and many interesting things have been done and are still being done.
All right. Thanks.
Okay, I'll request all of you to unmute yourself and thank the speaker. So you have to unmute yourself and thank you. Okay, thank you everyone. The next TPS is 15 July. Yogesh will be back for that one. And thanks a lot. Bye-bye.